The sun is dying right now. Not quickly, not in any way you'd notice in 1,000 lifetimes, but it's burning through roughly 600 million tons of hydrogen every single second, converting it to helium through a process so violent and so relentless that the light hitting your skin right now left that nuclear furnace 8 minutes ago. It traveled 93 million miles across the void of space just to reach you. That's our sun, the thing that makes all life possible, the object so enormous that 1,000,000 Earths could fit comfortably inside it. And yet, in the grand architecture of the cosmos, our sun is embarrassingly small. There are stars out there that make our sun look like a grain of sand next to a skyscraper. Stars so incomprehensibly large that the moment you try to visualize them, your brain quietly gives up and changes the subject. Stars that shouldn't exist according to our own marbles of physics. And yet they do, burning in the dark between galaxies, pulsating with energies that dwarf everything we've ever known. One of them was hiding from us for decades, hidden behind walls of cosmic dust, tucked inside a stellar cluster 20,000 light years from Earth, wrapped in layers of gas so thick that ordinary telescopes passed right over it without a second glance. It sat there, enormous and patient, radiating energy equivalent to hundreds of thousands of suns combined, and we had no idea. Until we looked in the right kind of light. What astronomers found when they finally saw it wasn't just a large star. It was a complete redefinition of what a star is even allowed to be. It forced physicists to revisit equations. It made stellar scientists question whether their models were fundamentally broken. It remains to this day the largest known star in the observable universe. Its name is Stephenson 2.8, and the moment you truly understand what that means, the universe will never feel the same again. Before we talk about Stephenson 2.18 specifically, we need to establish something important, something that makes this entire story more unsettling than it might first appear. Stars are not supposed to be this big. This isn't a casual observation. It's a mathematically supported boundary called the Eddington limit, a theoretical ceiling on how massive and luminous a star can become before its own radiation pressure begins tearing it apart from the inside out. Beyond this limit, the outward pressure of photons streaming from the core becomes stronger than the inward pull of gravity holding the star together. The result? The star begins shedding its outer layers, losing mass, shrinking back toward equilibrium. Nature, in other words, has a built-in size regulator for stars. Most massive stars never exceed 100 to 150 solar radii. Even the well-known stellar giants, the ones astronomers point to when they want to impress an audience, typically cap out somewhere in the range of several hundred solar radii under extraordinary circumstances. Stephenson 2.18 has a radius of approximately 2,150 times that of our Sun. That number is so far beyond the expected range that when researchers first calculated it, they ran the figures again and again. Because the instruments are sensitive, the measurements are complex, and making an error of this magnitude would be professionally catastrophic. But the numbers kept coming back the same. Something out there, in a dusty corner of the Scutum constellation, was genuinely this size. Consider what 2,150 solar radii actually means in physical space. Our Sun's radius is roughly 696,000 kilometers. Multiply that by 2,150. You get a star with a radius of approximately 1.5 billion kilometers. The distance from the Earth to the Sun, that vast 93 million mile gulf we just discussed, fits inside this star's radius more than 10 times over. Light, traveling at 300,000 kilometers per second, would take over an hour and a half just to cross from one side of this star to the other. If you replaced our Sun with Stephenson 2.18 tomorrow, the consequences would be immediate and total. Mercury would be inside the star. Venus would be inside the star, Earth. Along with every ocean, every mountain, every living thing that has ever existed on this planet would be inside the star. Mars would vanish into the stellar interior. Even the asteroid belt separating Mars from Jupiter would be swallowed whole. The surface of this red hypergiant would sit somewhere near Jupiter's orbital path, consuming 5.2 astronomical units of space in every direction. Our entire inner solar system, gone, not destroyed by the star, absorbed by it the way a rising tide absorbs a sandcastle. Volume-wise, the comparison becomes even more staggering. You could fit approximately 10 billion suns inside Stephenson 218. 10 billion. That's more stars than exist in some entire dwarf galaxies packed into the volume of a single stellar object. Here's the part of the story that deserves more attention than it typically gets. We almost never found it. Stephenson 218 sits inside Stephenson 2, a dense, massive star cluster discovered by American astronomer Charles Bruce Stephenson in 1990 during a survey of infrared sources in the Milky Way. Stephenson was cataloging objects that radiated powerfully in infrared light, a category of light that penetrates dust clouds far more effectively than visible wavelengths. His surveys were part of a broader effort to understand what was hiding behind the dense dust lanes crisscrossing the galactic plane. The galactic plane is a problem. The Milky Way is not a clean, transparent structure. It's dense with interstellar dust, complex organic molecules, silicate grains, carbon compounds that scatter and absorb visible light before it can reach us. Peering to the center of our galaxy in visible light, and you see nothing but dark lanes and obstruction. This is why so many massive objects near the galactic center remained undiscovered until infrared astronomy matured as a field. Stephenson 2 is located near the galactic center, roughly 20,000 light-years away. The stars inside it are heavily obscured. When Stephenson cataloged the cluster, the full membership wasn't clear. The dust made precise identification difficult, and the sheer number of stars in that region of sky created significant confusion. Stephenson 2T8, designated as member number 18 of the cluster, wasn't immediately recognized as extraordinary. It appeared in various surveys as a bright infrared source. But infrared brightness alone doesn't tell you radius. It doesn't tell you distance precisely. And without an accurate distance measurement, you cannot accurately calculate size. The refinement of Stephenson 218's remarkable properties came gradually, as better instruments, better distance measurements from the Gaia Space Telescope, and improved stellar modeling techniques allowed astronomers to pin down exactly what they were looking at. Each successive measurement pushed the star's estimated radius higher. The 2020 analysis, placing it at 2,150 solar radii, came from a careful synthesis of infrared photometry, distance estimates, and stellar atmosphere modeling. And it placed Stephenson 218 firmly at the top of every known stellar size ranking. A star this large, this luminous, this extreme, and it spent decades hiding behind a curtain of cosmic dust, unremarkable in survey data, unrecognized for what it truly was. The universe is very, very good at keeping its most extraordinary secrets. To understand how a star gets this big, you need to understand the life cycle that produces red hypergiants in the first place. Stars are born from collapsing clouds of gas and dust, predominantly hydrogen, with helium and trace amounts of heavier elements mixed in. As the cloud collapses under its own gravity, it heats up. When the core temperature reaches roughly 10 million degrees Celsius, hydrogen nuclei begin fusing together to form helium. The energy released by this fusion creates outward pressure that counterbalances the inward pull of gravity. The star reaches equilibrium and enters what astronomers call the main sequence, the long, stable middle period of stellar life. For the Sun, this phase lasts about 10 billion years. We're roughly halfway through it. But for stars many times more massive than the Sun, this process runs dramatically faster. The more massive a star is, the hotter its core burns, and the more rapidly it consumes its hydrogen. A star 20 times more massive than the Sun might exhaust its hydrogen in only a few million years, a cosmic eye blink. When the hydrogen runs out, the core contracts. The outer layers of the star, no longer supported by hydrogen fusion in the core, respond by expanding dramatically. The star swells outward into a giant, then potentially a supergiant, then, for the most massive and evolved stars, into a hypergiant. As it expands, its surface temperature drops. Hot blue light gives way to the cooler, deeper red that characterizes evolved giants. The star becomes what we call a red supergiant or red hypergiant. This is what Stephenson 218 is, a star in an extreme late stage of stellar evolution, bloated to incomprehensible proportions by the physics of its own dying core. It is burning through the last stages of nuclear fuel, fusing elements and shells surrounding the core, puffing itself outward while simultaneously pouring enormous amounts of mass back into space through stellar winds. Stars like this are inherently unstable. They pulsate, expanding and contracting over periods of months or years. They shed mass in torrent, creating expanding shells of gas and dust that surround them and partially obscure them. This is why Stephenson 218 is so difficult to observe clearly. It is literally surrounded by the material it has been expelling throughout its evolution. To appreciate where Stephenson 288 sits in the hierarchy of known stellar giants, it helps to meet the others, the runners-up that were, until recently, considered candidates for the largest star title. Scuti was for years considered the frontrunner. Located approximately 9,500 light-years away in the constellation Scutum, Scuti has a radius of around 1,500 solar radii. Extraordinary by any standard. It's luminous enough that if it replaced our Sun, it too would engulf the inner solar system. But revised distance measurements over the past decade have repeatedly nudged its estimated radius downward, and it now sits clearly behind Stephenson 218 in the size ranking. Levi Canis Majoris occupies a similar position. A massive red hypergiant in the constellation Canis Major, with a radius somewhere between 1,400 and 2,000 solar radii depending on the measurement technique used. Levi Canis Majoris is perhaps better studied than Stephenson 218 because it's less obscured by dust, and it has been tracked actively shedding enormous quantities of mass. Some estimates suggest it has lost the equivalent of multiple solar masses worth of material into surrounding space. It is, in the most literal sense, dying spectacularly and slowly in front of us. NML Cygni, Mu Cephei, or W Cephei, these are all candidates for the upper reaches of stellar size, all enormous beyond easy comprehension, all dwarfed by Stephenson 218's estimated dimensions. The crucial caveat in every one of these comparisons is uncertainty. Measuring the size of a distant star is not a simple process. You cannot extend the measuring tape across 20,000 light-years. Instead, astronomers use angular diameter measurements, distance estimates, which carry their own uncertainties, and stellar models to infer physical size. What isn't in serious doubt is that Stephenson 218 belongs in an elite category of stellar objects, massive beyond easy description, evolved beyond most known stars, and sitting at the outer boundary of what physics allows a star to become. Stars like Stephenson 218 don't fade quietly. When a red hypergiant of this mass finally exhausts its remaining nuclear fuel sources, helium, carbon, oxygen, silicon, building through the nuclear fusion chain to iron, the process accelerates toward a terminus that is almost theatrical in its violence. Iron is the endpoint of productive stellar fusion. Fusing elements lighter than iron releases energy. Fusing iron absorbs it. Once an iron core begins to accumulate in the stellar center, there is no further energy source to resist gravity. The core collapses in under a second, faster than any intuitive sense of fast can capture. In that collapse, a sphere of iron roughly the size of Earth compresses down to a sphere roughly 20 kilometers across. An object of such density that a teaspoon of its material would weigh hundreds of millions of tons. The rebound from this collapse sends a shock wave outward through the star at a significant fraction of the speed of light. The result is a supernova, a detonation so energetic that for days or weeks, a single dying star can outshine an entire galaxy of 200 billion stars. The shock wave expels the outer layers of the star, all that hydrogen, helium, oxygen, carbon, silicon, iron, and dozens of other elements forged to the stellar furnace across millions of years, out into the surrounding space. These expelled elements become part of the interstellar medium. They drift, they cool, they mix with hydrogen clouds. Eventually, over millions of years, they may be swept up in the collapse of a new star-forming nebula. They become part of new solar systems. They end up in planets, in oceans, in living cells. Every iron atom in your blood was forged in the core of a dying star. Every calcium atom in your bones, every oxygen atom cycling through your lungs right now originated in stellar nucleosynthesis, in reactions exactly like the one Stephenson 218 is currently running through in its ancient, bloated core. We live in a mote of rock orbiting a thoroughly ordinary star in the outer suburbs of a middle-aged spiral galaxy. By almost any cosmic measure, we are unremarkable. The universe contains roughly 2 trillion galaxies, each holding hundreds of billions of stars. The odds that anything about our specific location is special are vanishingly small. And yet, there is something remarkable about the fact that we can look up, we can point infrared telescopes at a dusty star cluster, 20,000 light years away, and through careful analysis, discover that one of the objects hiding in that cluster is the largest star we've ever found. We can run the numbers, check them, recheck them, and publish them for every other human on Earth to read and examine and challenge. We can stand on this ordinary rock and measure the architecture of a universe 13.8 billion years old. Stephenson 218 doesn't know we exist. It doesn't know it's the largest known star. It doesn't experience its own luminosity or feel the mass it sheds into space each year. It simply is burning, pulsating, expanding imperceptibly, moving toward the inevitable collapse that will one day scatter its elements across the galaxy. But we know it's there. We found it, tucked behind its curtain of dust, and we measured it, and we understood what it was. We took the universe's largest secret in that particular corner of the Scutum constellation, and we brought it into human knowledge. That's not nothing. That might, in fact, be everything. Because the atoms in the mind that's reading this right now, the neurons firing, the synapses connecting, the electrochemical cascades that constitute thought and wonder and curiosity, those atoms were made in stars. Stars that lived and burned and died so that eventually, billions of years later, the universe could produce something capable of looking back at it. Stephenson 218 will die one day. It will explode with incomprehensible violence, and its remnants will drift across the galaxy, and some fraction of what it's made of may eventually become part of worlds we cannot imagine yet. But right now, it's out there. 20,000 light years away, in the constellation Scutum, larger than anything else we've found in the sky.